data, the big elephant in the room. And the starting point for this research is regulatory compliance checking, because before any construction activities, we first need to check whether a building complies with regulations. And there's so many of them. And especially during the early design stages of a building, it's super complex to check all these while designing a building. One of the main reasons for this is because there's so many geometry complexities in these. Let's, for example, take one of the regulations that we just saw. This is one from the Dutch building codes. Material used on the inside of a shaft, bordering one or more fire compartments with an internal cross-section, blah, 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 should comply with a fire class, but not if that shaft is intended for one or more toilet rooms located above each other, and the thing does not pass through other rooms, 5% of, etc. So one article contains 7 of these relatively complex geometrical computations, and we have hundreds of these articles. And not alone is the geometry complex, the information that we need to create these computations exists in multiple files typically. So the shaft is in a different IFC file than the compartments and the walls. We've seen that semantic web technologies can deal with the heterogeneity, or some of the heterogeneity, at least the semantic heterogeneity of these, but geometry was typically difficult. There's I'd say four ways to deal with geometry in linked building data. One is using dedicated geometry ontologies, for example, GeoSparkle, so we can say that something has volume. One is non-geometry ontologies that also have geometrical concepts. For example, real estate core is not per se geometrical, but they have this volume thing. We can put non-RDF geometry, such as in this case well-known text, in RDF literals. And we can, in the RDF graph, refer to files. So we can say, we don't have geometry in the graph, but it's there in that IFC file, right? The right side, your left side, is nice because you can use geometry together with the semantic capabilities and with Sparkle and SHACL, etc. But storing that in a graph is not so nice. It doesn't scale really well. The left side is nice because it scales better, but you don't have that semantic capabilities. So we thought, can we combine this? Can we combine the semantic capabilities of linked building data with the geometric capabilities that we can get through IfcOpenShell? And we developed this thing that we call geometry engine, which basically communicates between linked building data graphs and IFC files, which works as follows. We select a linked building data graph from the linked building data graph on the left, and then we query IFC file paths that are in that linked building data graph. It returns these file paths and then patches these files. So it selects the IFC files there. Then we query whatever we want to query. We query elements, we query zones from the linked building data graph, and we can use a Sparkle query for this. That can be as complex as you wish. So you can also use non-IFC data in that Sparkle query. Then using those GUIDs, we go back to the IFC files again, and with IfcOpenShell open those specific elements that relate to that graph or to that query. Then using those IfcOpenShell elements, we perform geometric computations, and then we extend the elements that we got from the graph with the results of that geometric computation and store that in the graph again. I'll show you how that works later. So based on that methodology, we built this geometry engine in Python, which runs on top of RDFlib and IfcOpenShell. And we built, at this point, 10 functions that can help us to calculate geometries of things in linked building data graphs. So we can calculate the length, the width, the height in the area, etc. So simple stuff. But we can also do a bit more complex things like the distance between elements, whether they clash and what type of clash they do, and whether elements are in zones or zones are in zones, etc. So as an example, if you want to calculate the volume of an element, we query that element first. In this case, we query all the bot elements in a graph and its GUID. And then we run this function that we provide in the geometry engine. So first we define the function, then we open the IFC files using IfcOpenShell. We open the graph, the linked building data graph, using RDFlib. Then we query that query that I just showed, so we ask for all the elements and the GUIDs. And then using those GUIDs, we open the elements in the IfcOpenShell, so in the IFC. Then using IfcOpenShell, we calculate the volume of those elements, and then we store the volume in a new triple in the graph again. And the result is as simple as this. So we have an element with a volume and then a number. So we can do that for all these 10 functions that we just set. So as a case study, this is a Dutch fire safety regulation. An enclosed space is located in a fire compartment, so again, some kind of a geometric computation, but not if and then some semantic information. But then again, there is some geometric computation nested in that as well. So what we do is we convert that regulatory text to SHACL. So this is the same thing as this, but then in a machine-readable format. And in that SHACL shape, you can see that there's these two geometric computations are also there. So it asks for a space that intersects with the fire compartment, and it says that the usage area of a technical room can only be 50. Well, let's focus on the first thing. So what we do is we first query from our link building data graph all the spaces using bot space and all the fire compartments using self-created class fire compartment and their GUIDs. Then we run one of those functions where we just walk through, right? So we open these files, you put those GUIDs in IfcOpenShell, we check whether they intersect, yes or no. And if yes, it creates these added triples. So in this case, the storage room is inside the fire compartment, so it creates this triple intersects with the fire compartment. We also deliberately created some rooms that were outside the fire compartment. For example, here the living room was not inside the fire compartment. So this triple is not created for the living room. And then if we run that SHACL shape against our link building data graph, you can see that we get this violation. So it says this space is not inside the fire compartment. So this is a way to check whether you comply with the regulations. To conclude, with this geometry engine, we try to bridge the semantic capabilities of link building data with the geometric capabilities of IfcOpenShell in a very easy Python script. And future work is, well, first of all, to extend the Python functions. So I'd really like to know whether you have some functions that I can build, because it's there now. What I would also like to do is, find strategies to deal with the computationally heavy IFC parsing, because that's quite heavy in the beginning. Development as a user interface. We can now validate a building using SHACL, but it would be nice if we can also use that validation to then automatically generate things. For example, the living room was not inside the fire compartment. Can we then use IfcOpenShell to enlarge the fire compartment? Again, using the regulatory constraints that we have as machine-readable format. And finally, what would be nice is, last year we had these nice works in LDAC by Anna and also the bit softer geometrical representations of things. So I would really like to map that using, for example, LLMs to the functions in this thing, so that we can, using natural language, ask for geometrical concepts in buildings and then get them in a graph. And that's it. Hope there's questions.